Okay, guys, I think I'm going to go ahead and get started. I hope that you can hear me all right. I hope that the screen behind me is easy to read today. Fingers crossed on that. Hopefully the internet is going to be good for us for our session. Hope that you guys are all doing well also, taking good care of yourself and keeping up with your classes and everything that I'm sure is putting a strain on your time. Let me just quickly tell you where we're at. I sent you an email a little while ago saying we're going to start chapter 9 today. We're going to do that in just a little bit after we do a little practice on the chapter 8 stuff. But we are really not too far from being finished. In fact, by the end of next week, we should have most of the material for the whole semester done. Keep in mind that 2 weeks from now, we have a midterm on on Tuesday. And then on Thursday, we'll mostly be reviewing for the final. I might have one little section to finish up still on that Thursday, but we'll be mostly done. I've put up all of the rest of the homework assignments for the rest of the semester now. After today's assignment, which is section 8.7, and that's due at 11 o'clock tonight, there are just 3 homeworks left, and all of them are relatively short. The one for next Tuesday is not bad at all. It shouldn't take you too long. The one for next Thursday might take a little bit longer, but I think you'll be able to get started on it even after today's class. So we're really getting close to the finish line. Also, Migrator has been really busy this week, and so we are a little behind on getting homeworks back to you. He assured me that his schedule is clearing up here in these next couple days, and I expect that I'll be able to email you guys back some of your older homeworks very soon, hopefully within the next day or two. So sorry I'm a little behind on that, but I'll pass back some homeworks through email, and I'll update the grades again on the website. So remember to keep checking that your grades are accurate as we go along. If you see any errors, just let me know. And also remember that your grade is really probably approximately 3% higher than what it says on the spreadsheet that I've posted. And that's because I have not reweighted your grade yet. I have not dropped your lowest homeworks yet. I'm going to drop your 2 lowest homeworks or that quiz we took. We did take 1 quiz, so I'm kind of counting that as a homework. So I'm just going to drop the 2 lowest of any of those things that you've done all semester long. So none of that has been factored in yet. So your grade is actually higher than what it says online right now. Okay. Are there any questions about any of that before we get going into this today? Okay, and of course I am recording this session. So if you have missed anything or if you're going to miss anything, by all means, later today, this will be posted on the class lectures tab of my 250B website. So you're always welcome to go back and review things again. So, all right. We're going to start today with a quick recap of what I explained on Tuesday, which is the variation of parameters method for solving differential equations. One thing to keep in mind here, guys, is that with variation of parameters, I'm only going to be asking you to solve second order equations by that method. It's because higher order differential equations, although you can use a variation of parameters procedure for them, it's much, much more tedious to do by hand. And I think we can get the idea of how this method works just with a second order equation. So this method will you're only going to see it for second order differential equations. And it is a alternative to the Annihilators method for doing step 2 of that 3-step process for solving a differential equation, a linear nth order differential equation, right? So step 1 was find the complementary function. Step 2 is to find y sub p. And this is what I call the particular solution to the differential equation. So these boxes over here on the right of my screen are really important for you to have down. The form of the particular solution when you're using this method is that y sub p is equal to u1 y1 plus u2 y2. And the formulas for u1 and u2, I sort of derived them off of that handout on Tuesday that I screen shared with you. But don't worry too much about, I'm not going to ask you to rederive the formulas, but you should definitely know these formulas. Be careful with the minus sign on the u1 formula. u2 does not have a minus sign, right? So there is a sign change, and also the subscripting. The u1 goes with the y2 in the numerator of the integral, and u2 goes with y1 in the numerator of that integral. The capital F, of course, that's just the function that's on the right-hand side of your differential equation. And the W is just the Wronskian, our good old Wronskian that we learned about a couple of classes ago. Okay, so these are the formulas you need to know. You've been working on it, hopefully, on the homework that you're turning in for tonight. But just in case, I have one more chance to practice here with a warm-up problem. And keep in mind, guys, on the midterm that we're going to have and on the final exam, the questions are not going to say use variation of parameters. Part of what you need to learn, and part of what I think is important for a student in this class, is among all of the different techniques and tools that we have, making a good choice for which tool to use. So we need to practice deciding what tool to use when we're solving differential equations. So here's an example of that. We have a differential equation, y double prime plus 4y prime plus 4y equals the ln of x divided by x e to the 2x. So I'm hoping everybody can see my screen clearly at this point. So because it's a higher order differential equation, it's a second order equation. So what that tells me is that that I'm not going to be using chapter 1. I'm going to be using things that come from other places. Sorry, I'm just going to, I realize that my chat setting is only open to private. So I'm going to make it so that everybody can talk to everybody here. Okay, sorry. So this is not a chapter 1 problem. This is clearly a second order differential equation. And we've really learned two methods for second order differential equations. And they are annihilators, which is in section 8.3, and this section here, which is 8.7, variation of parameters. Can somebody tell me which of those two methods would be better to use in solving this problem? Should we use annihilators or should we use variation of parameters? Variation of parameters. Brendan, that's absolutely right. Now, why do I know that I want to use variation of parameters here and not the annihilator method? Because this is the important part. We have to have this self-conversation about why we should use the method that we're going to use. So if you remember, in the annihilator table that I gave you guys, that I screen shared with you, we know how to annihilate powers of x, we know how to annihilate sines and cosines, and we know how to annihilate exponential functions, and products and sums and combinations of those. Nowhere in that annihilator table are you going to find ln of x. Taking derivatives of ln of x, especially when it's in a fraction, is going to be really difficult. I mean, you're not going to simplify anything by doing that, right? The derivatives are going to get very messy and nothing's going to get annihilated. So because I don't know the annihilator for capital F, that's why we're going to choose to use variation of parameters. And this is second order as well, which fits the condition up here that I mentioned earlier, that we would only learn this for second order equations. So we use variation of parameters And that is mostly based on the form of capital F. The way the capital F looks on the right-hand side is not well suited to annihilators. So let's use variation of parameters, okay? So let's get into it right here. I'm going to start with step 1. In step 1, of course, which works the same no matter what method you're ultimately going to use, what we have to do is write down the auxiliary equation for the left-hand side of our problem. So we're ignoring the capital F in step 1, and we're just looking on the left side here. So I'm going to get the auxiliary equation is going to be r squared plus 4r plus 4 equals 0, right? And that factors as r plus 2 quantity squared equals 0. If you don't see the factorization immediately in your head, you can always use the quadratic formula for it, right? So that's always another option. But in this case, it factors really nicely. And so we get a double root of -2. So -2 and -2. All right, so I can write down my complementary function. I'm going to call it y sub c of x. This is going to be c1, right? c1 times e to the -2x, and then plus the second term is going to be c2 x e to the -2x. So there is the complementary function. We should put that into a box so we can find it later. And let me remind you that this first function here, this first one is what we're going to be calling y1 in our notation. That's y1. And the second function right here, this one is y2. So we have y1 and y2, which are the two sort of basis solutions that we can build this linear combination out of. So we have y1 and y2. We need those for the variation of parameters in step 2. Okay, so far so good. Just go ahead and feel free. I know we're doing this from 1,000 miles away, but just stop me if there's questions as we go along here. We're doing great, by the way, guys. We're not behind. I don't have to rush. I'm more than happy to take time to answer questions as we go. So don't hesitate. Okay, so this is really in section 8.2, step 1. Okay, let me come back up here and let's talk about step 2. Now, actually, the very first thing I like to do, just to kind of keep myself organized, is find the Wronskian. Because the W that I'm going to need in these formulas is something I have to calculate anyway. So let's do that first. Let's find the Wronskian. And this is the Wronskian of y1 and y2. So this would be the determinant of, I just remember how this works. We just put our functions on the top, right? So that's, I'm going to move this back just a little bit so there's a little more room there. So that's e to the negative, still don't have it quite. There we go. E to the -2x. And then the second column is x e to the -2x. Okay, and then I just have to take derivatives down the matrix. So when I take derivative of the first entry, I get -2 e to the -2x. And when I take the derivative of x e to the -2x, I have to use the product rule. So I'll get -2x e to the -2x plus e to the -2x. Okay? So hopefully that makes sense. This is just how we calculate the Wronskian. It's only a 2x2 determinant, so I can use my AD minus BC formula for the determinant here. So that's going to give me, let me write it up here in the top right corner. I might need 2 lines to do it. Let's see. E to the -2x times the lower right corner, -2x e to the -2x plus e to the -2x. All right, and then minus BC, which actually turns this into a plus. It becomes 2x e to the negative 2x times e to the negative 2x. And what you'll notice on that is that a lot of stuff is actually going to cancel. So I can cancel this with this. And after I do all of that, I'm left with just e to the negative 2x times e to the negative 2x, which is actually just e to the negative 4x. Okay, so the Wronskian in this problem is just e to the negative 4x. I just like to calculate that up front. That way I can go straight into my formulas for U1 and U2 now. Okay, so let's work them out. Let's work out U1. It's negative the integral of y2. y2 is down here on the bottom of the board here. It's just x e to the negative 2x. And then capital F. All right, I just erased the problem. The capital F is the function on the right-hand side of my differential equation. So in this case, that's going to be the ln of x divided by e to the 2x, or sorry, x e to the 2x, is that right? Yeah, x e to the 2x on the bottom. And then the other thing that we have to put on the bottom is the Wronskian, which is e to the negative 4x. Okay, so this is the first integral that we have to calculate. And the nice thing about this one is that the exponentials all cancel. They completely cancel. E to the negative 2x, e to the 2x, and e to the negative 4x on the bottom. It all cancels out. And the x's also cancel. So you're just left with negative the integral of the ln of x dx. Not bad, right? The integral of ln of x is actually in the table of integrals that you guys will have for your exams. And I'm just going to tell you what it is. Normally, you would solve it by, I think, integration by parts. But in this case, we can just go straight to the answer. We're going to get x ln of x minus x. When you find u1, you don't have to put a plus c on this antiderivative, because we're in the process of finding one particular solution right now. That's what this whole step 2 is about. So it's perfectly okay to just ignore the plus c when you're doing the U1 and the U2. Okay, so we've got U1 right here. Let me see if I can possibly, I don't have a huge amount of room, but let me see if I can, maybe I can make a little more room. Let me see if I can write down U2. Okay, so U2 is positive the integral of y1, which was e to the negative 2x. And then the capital F is still the same, ln of x divided by x e to the 2x. And then we have our Wronskian again, which was e to the negative 4x. Okay, so there's my integral. I hope everybody can read it all right. This is the integral for U2. There's no minus sign like there was with U1. It just comes from these formulas that we introduced on Tuesday. Okay? Again, the exponentials cancel. This time we're left with the integral of ln of x over x dx. How do you do that integral? ln of x over x. So you see, this is one of the problems of the variation of parameters method is you have to be able to do the integrals, right? At least with the annihilator method, you're not really doing any integration. But I do see some people putting some answers down. Paige, U substitution is exactly right. You don't really need integration by parts for this one. We can just do a U substitution where we let U equal the ln of x. The derivative of that is exactly 1 over x dx, right? So this is really just U du. So when you integrate U du, what you're going to get is the ln of x squared all over 2. In other words, U squared over 2. Right. So, and again, we don't need a plus c on the end of that. So there is your U2 formula. Okay. So if everybody's good with that. So guys, you do have to be able to do some basic integrals. okay? I am going to give you that table of integrals. It's on that handout, so you'll know which integrals, you know, I expect you to be able to do cold and which ones you can refer to the table for, okay? But basic U substitutions should be on your radar, right? Those we've seen those quite often. Okay, once we've got U1 and U2, we can go ahead and write down our particular solution. I erased the formula for it, but it was in the box at the beginning of our class today. U1, Y1 plus U2, Y2. So let's just copy everything down. U1 is negative ln x minus x, right? I'm sorry, negative x ln x minus x times y1, which was e to the negative 2x, okay? And then plus u2, which is 1/2 of the ln of x squared times y2, which is x e to the negative 2x. So there is the answer. Kind of I put it right above the complementary function. Okay. So again, this is just u1 y1 plus u2 y2. This is the particular solution. And now, finally, step 3 is where we add everything together. And I'm perfectly okay if you want to just, if you just simply want to write down the final answer. The final answer would just be y of x equals y sub c of x plus y sub p of x. When you're doing the homework and checking answers with the back of the book, you know, they're going to be adding all these terms together, right? And they might actually do some combining of terms. So just be aware that the back of the book is always trying to save space. As a co-author of that book, I know this very well. The publishers are trying to use less pages, so they will often cram the answers into some kind of a factored form. So you may have to do a little algebra to sort of see how all of your terms match up with what's in the back of the book in some cases. Okay, but this is the final answer. There's no need to do that algebraic simplification if you don't want to. This is perfectly fine just like this. Are there any questions about this example? We good? Okay, it's pretty easy. It's pretty easy. The hardest part is just figuring out that you need to use variation of parameters in the first place. Occasionally the integrations can be a little bit interesting, but beyond that, as long as you know the formulas for U1 and U2 and y sub p, you're going to be in good shape. It's not so terrible. Okay, I'm going to go ahead and give you one more practice problem here, and then I think we're going to be in pretty good shape. And we'll move on. So let's do one more. This is warm-up number 2. And again, I want to find the general solution. Okay, and so let me write down the equation that we're going to work with here. Y quadruple prime, so that's y with 4 derivatives, plus 13y double prime plus 36y equals the sine of 4x. Okay, let's think about this problem real quick. By the way, both of these warm-up problems are on group work number 14. So we're just doing a group work together like I've been tending to do lately. Now that we're going on virtual learning, I've been kind of skipping the group works and just doing them with you. So looking at that problem, what method do you recommend that we use to solve this one? This is the important question. Like, how are we going to go forward? Is this going to be solved by variation of parameters? So I've got a couple of good comments in the chat. So let me repeat those for everybody in case you're not able to see those. This is a fourth order differential equation. So if you remember a few minutes ago, I said we're not going to do variation of parameters unless it's second order. So this is not a variation of parameters problem. And in fact, if we look at the right-hand side, Randy made a really good point. This sine function is something that we know how to annihilate. Sines and cosines are in that annihilator table. So those are the two big clues that we should solve this one with annihilators. Okay, so we're going to use annihilators for the solution. So I'll just write that here so we're keeping track of our method. But yeah, knowing the right technique to use is really important. So this one is an annihilator problem. So my step one is, as always, we have to figure out the auxiliary equation. So this one, we just turn all of the derivatives into powers of r, right? So this is, I mean, I could write let me just remind you, there is an operator way of writing this using the capital D notation, right? So d to the fourth plus 13d squared plus 36. All of those d's just get turned into r's right here. R to the fourth plus 13r squared plus 36 is equal to 0. Right? So we just turn all the d's into r's. Every single time, that's exactly what's going to happen. Now, this is a fourth degree polynomial. So when I do this one in class normally as a group work, people sometimes get a little stuck on how to factor this one. But it turns out that it's not so hard to factor this one, because let's suppose for a second that we had the polynomial with the same coefficients, but with just a quadratic. Say we had x squared plus 13x plus 36 equals 0, right? So it's kind of the same form as this one. Probably everybody would be able to factor this one pretty easily in their head. It's just x plus 4 times x plus 9, right? So if we take advantage of that observation here in the context of a quadratic, we can actually apply that to this one as well. And the way it is going to work, though, is that the role of x is going to be played by r squared. You see that? It's like 13r squared is the same as 13x. So the x is just like r squared here. So this is going to factor as r squared plus 4 times r squared plus 9. Guys, you have to trust me that I'm going to give you things that are reasonable to factor, right, in the homework and on the exams, because if you can't factor the auxiliary equation and the roots are all messed up, it's going to be very hard to really proceed through the demonstration of the annihilator method. So you've got to trust me. I'm going to give you something reasonable. I think this one is reasonable. I mean, it is fourth degree, but I think it's reasonable. I think the factorization is fairly natural here. Okay. Now, if we look at this first term, this first part, r squared plus 4, the roots of that are going to be imaginary, right? These roots are going to be plus and minus 2i. And then on the second term, we're going to have r equals plus and minus 3i. So this is what we're actually going to end up with. Okay? So we have 4 roots. And now from that, we can write down the complementary function. So let me do that. The complementary function is going to be C1 times, now with the imaginary root plus and minus 2i, we're going to get a cosine and a sine, right? 2 terms with cosine and sine of 2x. So let's write that down. Cosine of 2x plus C2 times the sine of 2x. And I'm going to keep going because I have to do the other pair of roots as well, plus and minus 3i. So this is going to give me C3 times the cosine of 3x plus C4 times the sine of 3x. So there is the complementary function. It has 4 terms in it this time. Okay? So hopefully everybody can read my writing so far. Hopefully it's good enough. That's step 1. Let's put a box around that so we don't lose track of this first part of our problem. And now let's go on to step 2. So for step 2, we are going to use annihilators. So the annihilator of capital F is what I'm referring to, right? So capital F here is sine of 4x. So we have to think about what would it take to annihilate that. If I want to annihilate the sine of 4x, you can either think about that one in your head. It's not that hard to get it right, or you can just use that table that I keep talking about, and I've screen shared it with you a couple of times. I'm not going to pull it up again right now, but you can look it up. The annihilator is d squared plus 16. Okay, d squared plus 16, and that means that we get new roots, and the new roots that we get, I'll call those r again, are just the roots of r squared plus 16 equals 0, and that's going to be plus and minus 4i. These roots here, plus and minus 4i, that are coming from this quadratic, they are not repeats of anything that we had earlier in step 1. So these are completely new roots. Good enough. That means we can go straight to the particular, the form. I'll call this the form. I'm going to write down the form of the particular solution right now. Okay, instead of C1, C2, C3, C4, though, I'm going to call these constants capital A. So it'll be capital A times the cosine of 4x, and then capital B times the sine of 4x. So this is the form of the particular solution. Everybody with me? Okay, let me do a little erasing on the top half of the board here. Notice that this question does not just say find the form. If you read the question, it says find the general solution. Sometimes the book or the problems will allow you to just leave your constants A and B in your answer. But on this problem, they actually want us to carry it out. So let's see if we can. Except I just did a bad thing. I just erased my differential equation. Let me squeeze it up here in the corner again. So all of that equals the sine of 4x. Okay, so that's my problem. And that means I actually, to plug this form into the differential equation, I will have to take 4 derivatives of it. Okay, so this is going to get a little bit tedious. Let's just go through it. It's not that bad, actually. It sounds like it's going to be bad, but these functions down here are not very hard to differentiate. Okay, so for example, the first derivative of the formula at the bottom is going to be negative 4a times the sine of 4x plus 4b times the cosine of 4x. Okay, so factors of 4 are coming out. And then let's take the second derivative. We just bring down factors of 4 again, so we're going to get 16. So negative 16a times the cosine of 4x. And then minus 16b times the sine of 4x. Okay, hopefully I'm not going too fast. This is not hard work. This is just a little bit tedious to take all these derivatives. Okay. The third derivative is going to be 64a times the sine of 4x, and then minus 64b times the cosine of 4x. And finally, the fourth derivative, take one more derivative here, I'm going to get 256a times the cosine of 4x plus 256b times the sine of 4x. Okay, so we just calculated all of those derivatives of our particular solution. I like to just do that first, collect them all together, and then I'm going to start plugging them into the spots on the left side of my problem, of my differential equation. So now I'm going to do the plug-in step, and this is where I wish I had a much bigger board to work with, but I'll try to squeeze this in here as best I can. We're going to get the fourth derivative of y, which is this last line right here, 256a cosine of 4x plus 256b times the sine of 4x. So start with that. And then plus 13 times y double prime. Here's y double prime right here. I'm circling it. 13 times that. Just as a little hint, 16 times 13, because you see the 16s here. When you multiply by 13, that becomes 208. 208. So let's add 13 times this. It means it's actually going to be, so plus negative 208a cosine of 4x, and then minus 208b times the sine of 4x. Okay, and then finally, I'll go to a second line here. 36 times the original y, so that's 36a cosine of 4x plus 36b times the sine of 4x. So all of that in the middle, and I'm sorry, I'm going to try to help you focus your attention here. Right in the middle here, all of that, right, all of that has to equal the sine of 4x. Sine of 4x. Okay. So let me just come up here. I don't think we need this differential equation any longer. So I'm going to use this top right corner to just try to simplify all of this. If you look at the cosine terms, right, there's 256. So here's a cosine term, 256a minus 208a and 36a. If you actually combine those three terms together, you're going to get 84a times the cosine of 4x. Okay, so 256 minus 208 plus 36 comes out to 84. Okay, and then the exact same coefficient comes out in front of the b sine of 4x. So we're going to get also 84b sine of 4x. All of that is supposed to equal the sine of 4x, which is on the right-hand side of my equation. Okay? So can somebody tell me then, based on all of that, what is A? So looking at this equation, we have a cosine term and a sine term. I've kind of grouped I put all the cosines together, I put all of the sines together, and I'm matching up the left side and the right side of my equal sign. So there's no cosines on the right side. So the A had better be 0. A is 0. And maybe somebody I haven't heard from today by chance want to tell me what B is? What is B going to equal? Yep, 1 over 84. So 1 over 84 is the B value. So when we look at this particular solution down here, when we look at this particular solution here at the bottom of my board, the A is going to be 0 and the B is going to be 1 over 84. So this is going to end up being the final answer. 1 over 84 times the sine of 4x. That's it. Okay, so we have the complementary function, we have the particular solution, and so finally, last but not least, the final answer is just y sub c of x plus y sub p of x. And we can just put a box on that one as well. Okay, so there we have it. We've done 2 warm-up problems. One of them was with annihilators, that's this one, and then the other one was with the variation of parameters. Any questions at all on that example? Okay, if everybody's good on that, what I think I might do is I'm going to start chapter 9 right now. Okay. By the way, some of you may have questions on today's homework. I'm going to save that for until a little bit later. I want to start chapter 9 right now. Okay. So let me go ahead and erase everything. If you need to, you can watch my recording later, go back and review this again. But as I advertised in my email to you guys this morning, this chapter 9 is really what it's all about. It's really the punchline, the climax, whatever word you want to use for Math 250B, right? So we wouldn't be very happy if we stopped right where we're at. We need to cover this next chapter, which is really the highlight of the whole entire semester. And so we're going to have a couple, 2-3 weeks to go through this. So chapter 9 is called Linear Systems of Differential Equations. So let me give you a physical problem to kind of motivate this for you a little bit before we actually get into the heavy math of it. On Tuesday, I gave you a physical problem that represents where a second order, homogeneous linear differential equation comes up, the mass oscillating on a spring. If you remember right at the end of class on Tuesday, I gave you as a nice engineering application, you can have masses oscillating on springs and a differential equation would govern that. If you actually decide to hook 2 masses and 2 springs into a sort of a system of masses that are bouncing back and forth with springs between them, you're then actually going to be talking about a system of differential equations. Because you have more than one unknown function at that point. You want to know where is mass 1 physically in space and where is mass 2 physically in space at any time t. So systems of springs and masses is a wonderful application of this topic. But I'm going to give you a slightly different one that is reminiscent for you, hopefully, of something we did way back in January, right at the beginning of the semester. So here's an example to motivate. And so if you don't like the spring mass example, here's another one. Do you remember this problem where we had a tank and we had some chemical? This goes way back to chapter 1. We have some chemical, some amount of chemical in this tank at any time t, right? So we had sort of this faucet that was sending chemical into the tank at a certain rate and a certain concentration. And then out of the bottom of this tank, we had a leak with a certain rate and concentration of the chemical coming out of the tank. And there was a differential equation for this way back in chapter 1, a differential equation that models the amount of chemical in this tank at any time. And in fact, we even did some examples and we solved some problems with this setup. Now imagine, I'm going to change the problem now just a little bit. Imagine that we have a second tank over here. Let's take a second tank. I'm going to call this B of t. So a second tank, and we're also pouring stuff into this tank. Maybe I'll call this R1 prime and C1 prime. So put little primes on your inflow rates and in concentration rates. And maybe there's also some leak out the bottom of this one, which might be R2 prime, C2 prime. So we have a differential equation for this problem, right? The way I've drawn this picture so far, we have two separate problems. They are not related to each other. And so we could solve this one like we did in chapter 1. We could solve this one like we did in chapter 1, and everything would be fine. But what if there was actually a connection? Let's say there's a pipe here connecting these two tanks together now, and that it's possible for the solution to flow between the two tanks, right? Now it gets more complicated because what's happening in the first tank affects the second tank and vice versa. And we have two unknown functions, not just one unknown function. We have two unknown functions that are each related to each other. This is a system of differential equations. This is something that we have not learned how to handle so far. We don't have a method for solving this kind of a problem yet. So many mathematical problems, such as the one I just drew here, many mathematical problems involve more than one, I'll just underline that, more than one unknown function, more than one unknown function, and these would be related by a differential equation. So many mathematical problems, such as this one, or such as multiple masses connected to multiple springs, right? They involve many unknown functions. And that's what chapter 9 is going to be about. So let me write down, we're not going to solve this yet. Obviously, I have to explain some of the math behind it. Let me start into that right now. We're going to take a break in just a few minutes, but let me start for a few minutes to set up the notation for this chapter. And then after we take a break, I'll come back and we'll really start getting into the theory of how all of this works, okay? So the first thing that we need is the definition. We need to have a definition for a linear system of differential equations. And I'll warn you right now that this is a little tedious. It's going to take the whole entire board to write it down, what's left of the board anyway. But we're just going to write it down once so we can see how it visually looks. And then I'm going to start compressing it into a much more compact and easy to write down format. Okay, so here it is, a linear system. A linear system of differential equations, okay, is of the form. Okay, so I'm going to write down how these equations are going to look, okay? So the first one, we have, let's say, x1 prime of t. By the way, in chapter 9, we will almost always be using t as our variable. So I know that that's a switch because in chapter 8, everything in chapter 8 was like y of x, okay? So in chapter 8, everything was y of x. In chapter 9, everything is going to be written more in the form of x of t. So it's a little bit of a notational adjustment here as we start this new chapter that you need to be aware that this is coming, okay? So I've got x1 prime of t, and here it is, a11 of t times x1 of t plus a12 of t times x2 of t plus dot, 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 plus a1n of t xn of t plus b1 of t. So like I said, it's a bit of writing. I hope that you guys can read that okay. I'll zoom it in a little bit for you. That's just the first equation, okay? So the first unknown function is x1 of t, and this is a differential equation for it. And it involves not only x1, but also x2, x3, x4, and so on. You see, we have all of these other unknowns that also have differential equations. So x2 has a derivative, and we can write down something like this: a2(1) of t, x1 of t, plus a2(2) of t, x2 of t, dot, 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 all the way up to a2n of t, xn of t, plus b2 of t. Okay? And this keeps going. This keeps going. I'm going to write dot, 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 dots all the way down. We have a lot of equations. The very last one, again, we're only writing this out one time, guys. I know this is a lot to write, but hopefully you can keep up with me here. The very last equation, xn prime of t, is just going to be an1 of t, x1 of t, plus an2 of t, x2 of t, plus dot, 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 plus ann of t, xn of t, plus bn of t. Oops. There it is. Okay, I managed to squeeze it all into the bottom half of my board. This is a system of n differential equations. And there are n unknown functions. Those unknown functions are x1, x2, x3, all the way up to xn. Those are the unknown functions that we're going to be trying to solve for. Okay, so that's a lot of notation. Let me start trying to find a nicer way to write this. Okay, so I'm sorry, I'm jiggling my screen around a little bit here. Let me go back to the top. I'm going to rewrite this linear system in a much better way. Okay. Any questions so far, guys? Feel free to unmute yourself and ask a question if you're not clear on something, or if you want, you can also type your questions in. Okay, so far all right. You know, this set of equations at the bottom looks like we could use a matrix for it, right? In fact, we could rewrite this. We could rewrite this as follows. On the left side here, you see on the left all of these derivatives of these functions. I could just write x1 prime, x2 prime, dot, 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 down to xn prime. I could just make that into a column vector. Just kind of collect all of those derivatives into a single column. And then what about the right side? Well, it turns out this A11, A12, A13, and so on, we can lay those out into a matrix. We can lay those out in the rows of a matrix. So A11, A12, I'm suppressing the t at this point. There's really functions of t everywhere, but I'm just focusing on the actual name of the coefficient, okay? So A11, A12, up to A1n. And if we imagine multiplying that by x1, x2, all the way up to xn, right, we actually get all of this stuff that I'm circling right now. Remember when you do your matrix multiplication, go across the row this way and then down the column this way. So that's what we've got here. A11, x1, A12, x2, all the way down to A1n, xn. That's exactly what I have circled. Of course, I also need to add a spot to put B1. So this B1 that's on the far right side, I'm just going to put it in a separate vector on the far right side. Okay, and then we can continue this way and fill in the rest of the matrix. So this is going to give me a second row, A21, A22, all the way up to A2n, and then way over here, I'm going to have B2. All right, and I just keep going like that filling out the whole thing. The last row is just AN1, AN2, up to ANN, and then I have BN in the bottom right corner of the vector on the far right. Okay? This is simply a matrix way of writing this messy linear system. Okay, but even that is still too messy. It's still too much, right? Okay, so I'm going to go even further. This column vector right here, every single entry is being differentiated. I can just write that as a vector with a derivative on it. So x vector prime. Guys, in this chapter, the vectors are coming back, the derivatives are, the matrices are coming back, all of the linear algebra is coming back. We had a little bit of a break in chapter 8 because everything there was kind of scalar oriented, but now the vectors are coming back. Please try to put arrows on top of your vectors, okay? This collection of constants right here, they're not really constants, they're functions of t, but all of those entries form an n by n matrix, which we're going to call capital A. And it's being multiplied by this column vector here, which is just the x vector itself. And then we add the b vector, which is just the vector that corresponds to all of the entries in that far right vector. And there is an even better way of writing our linear system. Well, it's easier anyway, right? And our goal here in chapter 9 is going to be to solve for the x vector. Solve for x. Now keep in mind, because this is a vector, solving for x means actually solving for all of these entries, right? Every one of these unknown functions. So we have lots of unknown functions in chapter 9. And at least in this notation, I'm calling them x1 of t, x2 of t, x3 of t, and so on. And they're all just written as a column here. And that's what we're hoping to solve for. Okay? Now, if this b vector, so let me just make a quick comment here about the b vector. If the b vector is the 0 vector, so if there really isn't a vector here being added on the far right, right, then the system is called, so if there's no b vector at all, if there's no extra functions that are being added onto the far right side, then this system is called, well, here we go again, the same word we've seen many times, homogeneous. In that case, the system is called homogeneous. So that word gets overused a little bit, but that's just the standard language in this theory, okay? So in this case, what we have in this case is that x prime is just equal to ax. Okay, so that is the system in this case. Until section 9.6, which by the way will be the very last section that we're going to cover. Until we get to section 9.6, we're going to assume that b is 0. Okay, so until 9.6, we assume that b is 0. We're not going to worry about it until we get right to the very end. It'll probably be my very last lecture of the semester. I'll come back and I'll talk about what do we do if b is not 0. Okay, but for the next 5 sections, basically 9.1 through 9.5, everything is going to be homogeneous, and we're just going to be looking at this problem right here in the top of the board. So the b is gone. right? Everybody following me? There's no B for right now. We're going to work on solving these kind of problems first and understanding the mathematics of that. And then at the very end, I'll come back and talk about what do we do if B is equal to 0. One of the beautiful things when B is equal to 0 right away is the following theorem. Let me write down this theorem. This is actually a really a very, very nice result. I'm going to write this theorem and then do the proof of the theorem. And then after that, we will take a 10-minute break like we usually do. Okay? So here is my theorem. The set S, I'll call it S, of solutions to x prime equals ax, and I want to emphasize that a is n by n here. By the way, the matrix A is always going to be square size in chapter 9, just like it was in chapter 3 when we did determinants. The matrices always had to be square size, right? And then again in chapter 7 when we did eigenvalues and eigenvectors, the matrices always had to be square size there as well. And now in chapter 9, again, the matrix capital A is always a square matrix. So the set of solutions to this equation, guess what? It forms, this is where the linear algebra is coming right back to, I mean, we already have the linear algebra just with the matrix representation of the problem. But now some of the theory gets even a little bit more tangled up with linear algebra because this forms an n-dimensional vector space. An n-dimensional vector space. Okay. That is always a good piece of news, right? That's always good news because when something forms a vector space, it means you can actually focus on finding a basis for it. Because a basis will span the whole thing, right? S will get spanned by this basis with n functions in it, as it turns out. So we don't have to find all of the solutions to the system. We just have to find a basis worth. And a basis worth would be n, linearly independent solutions. That's the idea. So let me actually write down the proof. This one is not very hard, and it's worth doing once, okay? So I'm actually going to write this proof here. It's kind of a good chance to review some stuff from earlier in the semester too, when we were doing some of this vector space stuff. To show that something forms a vector space, right? The first two axioms, the most important axioms, are the closure under addition and the closure under scalar multiplication. So I'm going to focus on that. So closure under addition, right? You guys remember back in chapter 4, we did a lot of these, right? Showing closure under addition. So I'm going to start with two things that are in S, and then I'm going to check after I add them together, is the result still in S? So let's do that. Now, what should my vectors look like? My vectors are these solutions. They are the x's here, right? These are these column vector x's. So let me call them, in this case, I'll use x1 and x2. Let those be in S. So those are in S. And then what does that mean? This means, well, if x1 and x2 are in S, it means that they are solutions to this differential equation, this linear system, right? The set S consists of the solutions to that system. So this means that x1 prime is equal to ax1 and x2 prime is equal to ax2. So both x1 and x2, I'll just actually put a box around that. Both of those solutions satisfy those boxes. And what we're trying to check, this is how we verify closure under addition. We're going to look at x1 plus x2, and we're going to see whether x1 plus x2 is in S, right? Meaning it has to satisfy this system. So let's check it out. Let's check this out. Let me know if I'm going too fast, guys. I'm going to take x1 plus x2 and check if it satisfies this system right here. That means I take the derivative of it, right? Now, of course, derivatives, as we've learned for a long time, respect addition. So I can actually break this one up as x1 prime plus x2 prime as two separate derivatives separated by the plus sign, right? But the thing is, we already know what x1 prime is, and we already know what x2 prime is. It's just coming from these boxes. So I can rewrite this as a x1 plus a x2. And I bet you know what I'm going to do next. ax1 plus ax2 can be, of course, combined. I can factor out the capital A, right? This is just a matrix. I can factor it out. All of this is perfectly legal in matrix algebra. So I can factor out the A on the left, right? So this is what we have. A times the quantity x1 plus x2. So look where we started. The derivative of x1 plus x2. And we showed that it's equal to A times x1, x2. Isn't that exactly what is required for something to be in S? When you take its derivative, it should equal A times it. It's exactly what we just showed here. So thus, x1 plus x2 is an element of S. All right, so that's pretty good. We've got closure under addition. And now I'm going to squeeze on the top of the board. This doesn't take very much writing. The closure under the scalar multiplication. This is great that we're reviewing this now. We do have a comprehensive final exam in this class, which means you're going to need to go back and review showing that something is a subspace. It's closed under addition and scalar multiplication. Okay? So maybe you remember how we would start this off in chapter 4 way back when, right? We would start off by saying something like this. Let x1 be as above. So we just take the same x1 from above and we take a scalar, which I'm going to call k. So for scalar multiplication, we have a scalar and we take one vector here. And then what I'm going to look at is I'm going to consider taking x1 and scalar multiplying it by k. I want to show that this guy is still in S, which means I have to take his derivative and see if it equals A times itself, right? So let's do it. Let's take the derivative. So we're taking the derivative of a constant times this vector. Okay, so constants, they can always come out, right? You can always factor out the k. So it's just going to be k times x1 prime. So put the prime just on the x1 by itself. And now, because x1 is as above, it means we have this. In this physical case, it's actually below. It's underneath me here, right? x1 prime is actually replaceable with ax1. So let's do that. We get k scalar multiplied by ax1. And be careful, guys, because this is a scalar and then a matrix and then a vector. So in chapter 9, it all gets kind of jumbled together. So we have a scalar, a matrix, and a vector. But what we really want to do is get the capital A out on the left. Now, normally, you can't switch matrices with other matrices. I'm sure you remember from chapter 2 that matrix multiplication is not commutative. However, this is not a matrix in front. This is a number. And whether you pre-multiply a number into a matrix or whether you take the matrix and then post-multiply by that number makes no difference. So you are certainly allowed to rewrite this as A times kx1. And I'm going to actually put the kx1 part together, because this shows me that the derivative of kx1 is just A times kx1. And that tells me, that implies that k times x1 is in fact an element of S. So S is closed under addition, it's closed under scalar multiplication, and the rest of the vector space axioms are just the usual algebra stuff that works for Rn. I mean, this is kind of like Rn, isn't it? The solution set. I mean, what are the vectors that we're looking at? They're like x1, x2, ... up to xn. This is like vectors in Rn, except these are functions inside of these slots. x1 is really a function of t. x2 is a function of t, and so on. So it behaves like Rn in that slot by slot sort of style, but the actual entries can be functions now. Right, we're solving for these functions actually. That's what we're going to be trying to do, to solve for what S is. So everywhere that, everywhere that you see a derivative on the board, it's always a derivative with respect to t. Notice that nowhere on this board do you see t anywhere. It's because we usually will suppress the t variable, and it kind of just hides in the background of our calculations, but that's really what's going on. So, okay, so I have a vector space. It turns out it's n-dimensional, and the great thing about this is that therefore to solve these linear systems, I'm going to be able to get away with simply finding a basis of solutions to my linear system. Are there any questions at all so far? Okay, if not, I would like, really for my sake more than anything, to take a short break. Let's take, it's about 1:15 right now. Let's take about almost 10 minutes, I think. There's nothing wrong with doing that. During this 10-minute break that I'm going to take right now, if you have questions that you'd like me to maybe work through with you on the homework that's due tonight, maybe you could type them into the chat for me. And that way, when I come back from the break, I'll sort of know which problems I should maybe open up for. So again, at about 1:25, I'll come back and we'll take a look at some of the homework problems. And we're also going to continue through a little bit more of chapter 9 as well. So don't go away, because I've got good stuff to share with you when we come back. All right, so 10-minute break. So Randy, if you're there, I noticed you wrote down 9.2 number 9. So that's not due until next Tuesday. The only problems that are due tonight are the 8.7 and then those 2 problems on page 575. So you might want to refresh your homework screen. I did originally have all of that together in one big assignment, but I decided to break it down into 2 smaller ones. So you have a kind of a short assignment due today and then also a short assignment due on Tuesday. So no worries. I gotta wait a couple more minutes and then we'll start back up again. Okay, guys, I think I'll go ahead and let's resume here. I hope that you're within the sound of my voice out there and can see what I'm doing here. I see there are a couple of questions on the homework that people have asked me. I'm going to do those at the end of the class today. Sometimes I do it in the middle, sometimes the beginning, sometimes the end. Today I'm going to do it right at the end. So I'm going to save about 10 minutes at the end to maybe work through those 2 examples. However, what I would like to do first for the next 15 minutes is just press a little further into this chapter 9 material that we just started because we're not that far from sort of having the whole foundational theory of it done, believe it or not. And that way next week, we'll be able to just fly right into the actual practical matter of how do you actually solve these systems. So far we haven't address that. I have not talked to you about how do you actually solve this linear system for x. We don't know how to do that yet. We do know, however, that those solutions, whatever they are, form an n-dimensional vector space. So the power behind that is that if something forms an n-dimensional vector space, I can span it with n linearly independent vectors, right? If I can find n solutions that are in S, if I can find n solutions to my system that are linearly independent, they are going to be a basis that span all of the solutions. And this is always the goal in linear algebra. Find a spanning set or a basis, right? These are the kind of questions you've heard me ask many, many times. right? So it does bring up a question though, because we are working with vector functions now, which is something we have not worked with until today. We really haven't worked with this type of vector where we have, you know, these columns of unknowns, where the entries in those columns are functions rather than just numbers. So a question does come up here, which is what I've put on the board. How are we going to be able to tell if n of these vector functions are linearly independent or not? What is going to be our tool for deciding that? It turns out that the answer to this question, the answer here is a very nice one. It turns out that we're going to use something that is also called the Wronskian. So I know we just learned about a Wronskian in chapter 8, but the answer here is a Wronskian, and it's not the same Wronskian. It's not the same Wronskian that we were looking at before. So let me write down the definition of this Wronskian, and then we'll do an example or two. Okay, so the definition is that the Wronskian of, let's say, x1 vector, x2 vector, and so on, up to xn vector. So again, please don't confuse this with chapter 8. These vectors here are actually vectors with slots. In chapter 8, we were looking at Wronskians of scalar functions, right? Remember, we made the matrix. How did we make the matrix for this Wronskian? We put our scalar functions on the top row, and then we just started taking derivatives down the matrix until it was square size. This Wronskian is completely different. Okay, it is still going to be a square matrix, and we're going to still take the determinant of it. But what this is it's very simple. You just lay your vectors x1 through xn into the columns right here. So you don't have to take any derivatives or anything. We're literally just going to come down column by column and fill out n columns to this matrix. And that will be a square matrix. And we just take that determinant. And again, there is a theorem that is very similar to the one in chapter 8. It really just says that if the Wronskian is not 0, okay, the determinant is not 0, which is a good thing, then the scalar functions will be linearly independent. So if, I'll write it down here for you guys, if there is a value, and the value this time would be in terms of t, right? So there is a t that is hiding behind everything that we're writing here. So if there's a constant t naught, if there's a fixed value t naught, such that the Wronskian of x1, x2, up to xn at t naught is not 0. So if this Wronskian can be made not 0 somewhere, then this is the theorem, x1, x2, and so on, up to xn is Li. Okay, so my functions will be Li. This is what we want, right? We want to have n linearly independent functions to serve as a basis for capital S. And the Wronskian is how we can check that. Let me just do a quick example of this. Okay, so this is our test for linear independence. It's called the Wronskian, just like it was in chapter 8. So here's an example. Is the following set, I'm going to make a set of vectors here. I'm going to draw them as columns. So t plus 1, t minus 1, and 2t. That's the first column. And then the second one is going to be e to the t, e to the 2t, e to the 3t. That's my second vector, comma. And then my third vector is going to be 1 sine of t cosine of t. Is that set Li? Okay, so I don't have a differential equation in mind right now. I'm just trying to get the hang of this Wronskian thing first, and then of course by next week we'll be putting this together with the differential equations to see the whole process as a complete whole. But for right now, I just want to practice this. So what I'm going to do to address this one is I'm going to try to write down my Wronskian right now. W, and these functions, by the way, we can call them x1, x2, and x3. Okay, so I have my 3 vector functions here. So the Wronskian of x1, x2, and x3, well, that's just going to be the determinant of the matrix. See, this is so simple. You don't even have to take any derivatives. You just recopy your columns into your matrix. It's just that easy. So it's going to be a matrix that consists of all of these functions of t. Okay, so here it is. There you go. So I hope everybody can see that. I kind of squeezed that into the middle there. All I did was lay these 3 column vectors into these columns right here. And this makes a square matrix on its own. We don't have to take derivatives or anything to make that happen, right? Now, the theorem says if there is a value of t naught such that the Wronskian is not 0, then we win, right? Then we're going to be happy with this. So the question is, do we have a value of t that we can use? One choice at this point would be to use the arrow method and just work out this determinant. It would be messy, right? Because you'd have, 6 arrows. Everything would be in terms of t. This matrix has no zeros in it, so it would be a little bit of a long expression, but you could do that. Or the other choice, sorry, we can choose to try to plug in a value of t. I need some water. We could try to plug in a value of t here. Like we could evaluate this. There comes my voice back, sorry. Just got some water down my windpipe, I think. I'm good. Thanks, guys. I'm doing excellent. Just happened for a second there. So this is some function of t. We can plug any number in for t that we want and see if we get lucky. Instead of trying to leave everything in terms of t, it might be easier to just plug in a number. So let's just try the easiest number that I know, which is 0. And when I do that, I might get unlucky here. Like this t value might not be the right one. But let's just try it. If we put in 0 for t, we're going to get, I'm just plugging 0 into all 9 of these functions here that are in this matrix. If I just do that all the way through the whole matrix, plugging in 0 for t, I just have to evaluate, e to the t, sine t, cosine t, all these things, just plug in 0. Now at least I have a matrix of numbers. And it's pretty easy to just take the determinant of that. And it turns out, I'll let you guys check this one, that this determinant is not 0. So we found a value of t that works. And so the answer to the question then at the top of the board is yes. My functions are definitely Li. Okay? If we had gotten 0 here, let's say we plugged in t equals 0 and we got 0 here. In that case, we might have to try another value of t. We could pick a different number, run through the calculation again, and try again to see if we can get a non-zero answer. If we keep doing that, if we keep trying different values of t and we keep getting 0 every single time, then we might suspect that our functions are actually LD. And in that case, what you could do is you could just take the determinant in terms of t and see if the whole thing cancels out, because that's actually what would happen. If the functions are LD, then no matter what t is, you can leave the t as a variable in your determinant, and as you evaluate the determinant, it would always cancel completely. That's for LD situations, okay? But here, we plugged in a value of t, we got lucky, the determinant was not 0, so by that theorem that I've erased, these functions are Li, okay? So far, so good. I'm going to, yeah, well, that's probably, okay, I'm gonna just tease you with, you know, my cliffhangers, right? I'm just gonna give you a quick little pointer on where we're going, and then I'm gonna turn to the homework problems. So far in all of this talking today, so you guys don't actually have to take any notes right here. This is literally 2 minutes, and then I'm gonna turn to the homework. So far in everything I have said today, we've been looking at this linear system, but we haven't been solving it, right? We've been talking about, you know, the fact that the solutions form a vector space, and, you know, if A is an n by n matrix, then we need to find n linearly independent solutions, right? And we just talked about this Wronskian, which is how we can test if our solutions are linearly independent. We've done all this background theory, and I appreciate you guys bearing with me as I've kind of done a lot of theory today. But we haven't actually dealt with the practical issue of how do you actually solve this thing, right? How do you actually solve it? So that's going to be where we're going to go next week, is how you solve it. And there is an amazing thing that happens. It turns out that the solutions to this system can basically be formulated by finding the eigenvalue, eigenvector pairs of the matrix. Chapter 9 is really going to bring everything together. And we're going to need eigenvalues and eigenvectors. We just saw determinants a few minutes ago. We're going to be finding null spaces, which means we're going to be solving systems of equations. It's all going to come back. This is the chapter where we use everything that we learned pretty much from the whole semester. So on Tuesday next week, I'll explain how the eigenvalue eigenvector pairs of this matrix can be used to actually solve the system. Okay, so it'll be a great opportunity to refresh our memory about eigenvalues and eigenvectors again. Incidentally, guys, already what I've said today, I have pretty much covered, I've more or less skipped section 9.1, and I've already covered 9.2 and 9.3. Okay, the material in 9.2 and 9.3, that includes the Wronskian, the vector space theoretical background, and kind of just setting this whole chapter up. So on Tuesday, we're going to start talking about section 9.4 and 9.5, which is where we actually work on solving these systems, okay? The homework that you're going to do for Tuesday on 9.2 and 9.3 is really pretty short. I'm guessing it will take everybody less than an hour, maybe even just a half hour. So this would be a good chance for you if you have some free time. And I know the pandemic is crazy and people are really busy and there's a lot going on. But if you have a bit of a break in your schedule, you could start looking at the midterm 3 review materials, because our third midterm is a week from Tuesday, and we've covered almost everything that is going to be on that midterm. So yeah, do the homework for Tuesday, which is a very short assignment on 9.2 and 9.3. But if you have a little extra time and want to get a leg up, this is a great chance to do it, because you won't be so busy with the homework and I think you'll have 5 days until I see you again that you could be working on starting to review for the midterm. Just a little piece of advice going forward. But this is a teaser for next Tuesday. I'll explain all of this in full detail. All right, so for now, I'm going to stop with that and spend the last 8 minutes or so looking at those homework problems that people had put on the board. Now, I think I've got to look at which ones those were. 8.7, number 6 was the first one that I saw there. So on 8.7, so this is the homework for tonight, the homework you're working on for tonight. If you're done with it and you don't have any questions on the homework, of course, you don't need to stick around. This is the only thing I'm going to do for the rest of today is look at these two problems. But you might want to watch it and see how I solve these things here. So we have this differential equation on number 6. It's a second order non-homogeneous equation. And so the first step, of course, is to write down the auxiliary equation. This is a little bit of a deceptive quadratic equation, though. It looks like it's going to factor easily, but then it doesn't. It actually does not factor nicely at all. You actually have to use complex numbers. When I use the quadratic formula on this, I get 4 plus or minus 16 minus 20 all over 2, which gives me roots of 2 plus or minus I. So 4 divided by 2 is 2, and the square root of negative 4 is 2I, but I have to divide that by 2 as well. So I get 2 plus or minus I. So my complementary function, actually let me write the complementary function up here at the top, is going to be C1 e to the 2x cosine of x plus C2 e to the 2x sine of x. Okay, so there's the complementary function on problem number 6 here. Just coming from the auxiliary equation, right? Like usual. Sorry, let me make sure you can read the whole board there. Okay. Step 2 is where we have to figure out the particular solution. If you look at your table of annihilators, you're not going to find tangent, right? This is not a function that we know how to annihilate. And that's my reason for using variation of parameters, okay? Don't just use it because we're in section 8.7, right? We have to understand, why are we using that technique? It's because the annihilator technique won't work here. So what we're going to need to do is we're going to need to find our Wronskian for this set of basic functions here. So I've got e to the 2x cosine x, e to the 2x sine x, and then we take the derivatives of those. This is kind of messy. I'd rather not spend 5 minutes just taking this determinant. I think if I remember correctly, this comes out to well, I think this whole thing just comes out to e to the 4x. Does anybody have a confirmation on that? I'm pretty sure when you're going to get a cosine squared and a sine squared that basically is going to add up to 1 and cancel some terms. I think this is right. Let's try and see if it'll work. Let's use the U1 formula. Negative the integral of y2 f divided by the Wronskian. So this becomes negative the integral of e to the 2x sine of x times capital F, which is e to the 2x tangent of x, all divided by the Wronskian. And as I said, I believe the Wronskian is just e to the 4x. And now that I'm looking at this, I'm pretty sure that I have that right. So I'll let you check the determinant. It's e to the 4x, okay? And the reason that that's so nice is that all of these exponentials end up canceling. And so you're left with, for u1, you're left with negative the integral of sine times tangent. Now, how are you going to work with that? Well, the trick to doing that is to rewrite the tangent where you have this tangent of x right here. Rewrite it as sine over cosine. So you already have one factor of sine on top. Change this tangent to sine over cosine, and you'll have this fraction looking like this. And now you can use that identity. There's an identity that sine squared is 1 minus cosine squared. So I would recommend that you use that. So this is a good question. Whoever asked this question, this makes sense. This is a bit of work to figure out these integrals. To do this integral down here, you're going to want to split this fraction up, right? So I'm going to keep working on it right here. You're going to have negative the integral of 1 over cosine. Well, that's just secant. And then cosine squared over cosine is just cosine. So this is now the integral that you need to evaluate. And I would recommend that you just use your table of, use a table for the integral of secant. It's kind of messy. I'm pretty sure that the integral of secant is the ln of secant of x plus tangent of x. Let me just see. I have a table of integrals here. It'll be in there, I think. Yeah, that's right. The ln of the absolute value of the secant of x plus the tangent of x. And then, of course, the integral of cosine is just sine. Okay, so all of that is just u1. Right, that's just u1. Now, for u2, it's a little easier because for u2, so this is u1 right here. For u2, you're going to be doing the integral of y2. So that's e to the x sine of x times the capital F, which was e to the 2x tangent of x, and then all over e to the 4x. No, I'm sorry. I made a mistake. I'm going too fast. You know what I'm saying wrong? u2 is the integral of y1. I got that backwards. Here's y1 right here. This should be cosine of x this time. Sorry. I made the mistake I don't want you guys to make, right? u2 goes with y1, right? So we have u2 equals the integral of y1 times capital F all over the Wronskian. The Wronskian was e to the 4x. This one is much easier to integrate because cosine times tangent is just sine. So you're just integrating the sine of x, and that is just negative cosine of x. So there is u2. So have I done enough of this one for people? So you know what u1 is, you know what u2 is. So your particular solution, maybe can I avoid writing it all out? You guys can handle that. It's just u1 times y1 plus u2 times y2. Awesome. Okay. We are out of time in terms of our official class. It's like 1:50 right now. However, I'm going to do the other problem. I think Darian was the one who was asking this problem number 28 on page 575. So I'm just going to stick around. If you can stick around and want to watch, you can. But I won't be offended if you have to leave the room and go to another class. I totally get that. And you can always ask me more questions in my office hours later. But I think since we're all here right now, and I think maybe some people would like me to do number 28, I'm going to go ahead and do it. All right? Going to erase this. You can always look back and watch it later. But let me look at number 28. Now this one is the following problem on page 575. Y double prime plus 2y prime plus y equals 2x e to the negative x. And we're supposed to solve this one in two ways. We're supposed to do it using annihilators and also using variation of parameters. Does anybody have a preference, or maybe Darian, if you have a preference, which way I solve it first? We're going to get the same answer either way, but I just wonder if anybody cares. Would you like me to do annihilators first or variation of parameters first? We've got two ways to get this. Nobody cares? Okay. If nobody cares, let me do it the annihilators way, just to start off with, just because that's kind of the first technique we learn. So if we use annihilators, well, first of all, did everybody get the complementary function figured out? This is just r squared plus r squared plus 2r plus 1. The roots are just -1 and -1. So even without really doing any work at all, I already know that my complementary function here is going to be c1 e to the negative x plus c2 x e to the negative x. And that is useful for both the annihilator method and the variation of parameters method. Okay, so we've got that. I'm just going to trust that you guys are with me on that. I didn't probably show enough work, but that's just to sort of speed things up a little bit here. Okay, the annihilator of this right-hand side, remember that the 2 does not matter. And so I just have to go to my annihilator table and look up what is it going to take to annihilate x e to the negative x. Turns out, if you look at your table, you're going to see that the answer is d plus 1 squared. Okay, that's the annihilator of the function on the right. So my new roots are just -1 and -1. Again, those are actually repeats of the roots that gave us this complementary function. So these roots are coming up for what would be the third and fourth time, right? The third and fourth time that -1 is a root. So my particular solution, my form of my particular solution is going to be ax squared e to the negative x plus bx cubed e to the negative x. So we're stacking those x's pretty high right now because this root of -1 keeps repeating every single time. Okay? So this is the form of the particular solution, and we would need to take, what, 2 derivatives of it now. So if we take, I'm going to go ahead and do this. This is a little tedious, but for those of you who want to stick around, all 10 of you that are left, I'm going to go through it so we can check our work, okay? So for the first derivative, the a gets factored out. I just take the first term times the derivative of the second plus the second times the derivative of the first. And that's what I'm going to get right there. That's just the product rule. Okay? And then plus b times, I'm going to use the product rule on the second term as well. So I'm going to get -x cubed e to the negative x plus 3x squared e to the negative x. So there is my product rule for the second term. Great. That's just y prime, right? So we also have to figure out y double prime. So y double prime, you know what might be easier actually would be if I factor, you see that there's an e to the negative x that I can factor out of all of these terms. If we actually do that first, I think it will make it easier. So let me just do that right away here at the beginning. I'm going to take out e to the negative x outside of everything. And so then what I'm going to be left with is -ax squared plus 2ax minus bx cubed, and then plus 3bx squared. So all of that, right? So that's the first derivative. So factoring the e to the negative x is probably going to help us a little bit. Okay, so now I can find the second derivative. The second derivative is going to be the first term, which is e to the negative x, times the derivative of everything in the brackets, okay, which is negative 2ax plus 2a minus 3bx squared plus 6bx. All of that plus, okay, so that's the first term times the derivative of the second, plus the second term times the derivative of the first, which actually gives me minus. See, the derivative of e to the negative x is actually a minus sign. So what I'm going to do, I'm going to open that bracket back up again and factor the e to the negative x out of the second part of it as well. So minus, right? So it's going to be minus all of this, right, at this point. So when I do minus of all of this, I actually change all of these signs. So it's plus ax squared minus 2ax plus bx cubed minus 3bx squared. All of that. Okay. So that's the second derivative. Now we have to plug it all into the left side here, okay? And so when I do this, when I plug this in, I do not have nearly enough room on this board. It's going to be all of this stuff that I've already written down. I don't think I'll recopy it. I take all of that and I'm going to add to that 2 times y prime. So actually, I'm just going to do the plug-in right here. I'm sorry. This is a little bit messy. I can see why you wanted to ask me this one. It's just all the product rules get really tedious. So this is y double prime, and now I'm going to add 2 times y prime, which is actually 2 times this line. And I'm taking this e to the negative x out. So I'll get negative 2a x squared. So I'm just doubling this part in brackets here, right? Plus 4ax minus 2bx cubed plus 6bx squared. So I have doubled all of the terms from the y prime. And then finally, I have to add y. And here's what y was, the original particular solution. Let's take that e to the negative x and factor it right here with everything else. So I just have to add ax squared to bx cubed. So plus ax squared plus bx cubed. This is all some giant expression that is the left side of my differential equation. Now, there's a ton of cancellation, right? This bx cubed and this bx cubed cancels this negative 2bx cubed, right? And then I have 4ax, which cancels with negative 2ax and negative 2ax. I also have a minus 3bx squared, a minus 3bx squared, and a positive 6bx squared. Okay, and then I have ax squared, and 2ax squared being subtracted. All of that cancels. So if you look at this, the only things I did not cancel are the 2a and the 6b. And those circled parts are getting multiplied by e to the negative x. We're trying to match that up with the right side of the differential equation. On the right side, I have e to the negative x with a 2x in front of it. right? So this 2x has to match up with 2a plus 6bx. So let me write that down. 2a plus 6bx has to equal 2x. Okay, hopefully everybody is still with me. I haven't been hearing a lot from the peanut gallery out there. I hope that means that this is good. The 2a part is just 0. All right, so there's nothing there. And then 6bx has to equal 2x. So b is 1/3. So b is 1/3. So a is 0 and b is 1/3. And that is what you're going to put right here in this particular solution. Here it is. Just stick in a equal to 0 and b equal to 1/3. So the final answer for the particular solution is 1/3 x cubed e to the negative x. So this is the y sub p, and you're going to be adding that to the complementary function that's up there at the top. Darian, did you follow this? Great. How about everybody else? Are there any questions on this? It's a little messy, but look at all the cancellation that happens when you actually plug everything in. Pretty good? All right. I'm teaching math from 1,000 miles away and making some sense. This is a good thing. Now, we're supposed to also redo this problem using the variation of parameters method. Would you guys like me to resolve it using the variation of parameters method, or was this mainly the part that was getting people stuck? Okay, if people are pretty good with maybe I'll call this good. We practiced the variation of parameters quite a bit today. So I think I'll let you try the variation of parameters way of solving it. And of course, you should get the same answer. It may have to be algebraically manipulated to give you the same particular solution, but you should get a 1/3 x cubed e to the negative x as your particular solution. The complementary function will be the same, and you just have to run through those integrations, the variation of parameters approach. I'll let you try it on your own, and if you get stuck, stop by my office hours. I can certainly spend a little extra time and just work that part through with you as well. But I think for your practice, I'll let you try the variation of parameters method on your own. Okay, so with that, I am done for today with our formal class. Thank you guys for coming. Appreciate it. Let me know how I can help you out. We'll see you back here again next Tuesday. But keep in touch between now and Tuesday. If there's anything that you need help with, or if you start studying for the midterm and you've got some questions, know that you can always send me an email. We can always come into a Zoom room and chat a little bit. So, and I'll keep you posted about my office hours as we go along as well. So, all right. Thanks, guys. I will go ahead and end this meeting, and we will talk again very soon. Bye for now.